Good afternoon.
Good afternoon.
I'm very glad to welcome you at this summer school and my presentation. My name is Rynat Bahdanovich and I'm a senior lecturer at the Belarusian State University, PhD in nuclear engineering, or more precisely in nuclear reactor computer modeling. My today's presentation is dedicated to an overview of nuclear power. I hope it will help you to understand what is nuclear power, which major problems it faces today, which physics governs nuclear reactors, and why there is a need to develop nuclear power in the world scale. The information which I want to share with you was crucial for me to choose my professional path years ago. If you have any questions, please write them into the chat. First of all, let me introduce you the topics of the presentation. I will start from energy consumption and global issues. How are they connected? Do we need to produce more energy and electricity? Then I will talk about the advantages, issues, and prospects of nuclear energy. Is nuclear better than conventional sources of energy or renewable sources of energy? Do we need to produce new reactors? How dangerous they are? I will describe the main concepts of nuclear power reactors, which types of reactors we should build for sustainable development, what kind of physics governs the reactor. And in the final part, I will talk about nuclear power in the world. How spread are nuclear power reactors? Which countries build them? Which types of reactors are operating today? How many reactors operating in Russia? And before I start, let me ask you to think in the world scale. Does humanity need more energy? Or do you personally need more energy? And for what do you need this energy? Speaking about myself, first what comes into my mind is utilization of gadgets, commuting and traveling, preparing food and other daily living needs. In general, we need energy for life comfort and development. Also, we should add industrial needs, because all goods are produced with the use of energy. That is why, as the world's population will grow, the energy demand will grow. Here you can see how world's population and its annual growth rate have changed during the last 3 centuries. And also the projection for the current century. Today, the annual growth rate is around 1%, and it is slowly approaching to 0. As you may have noticed on the animation, the biggest growth of population is anticipated to be in Africa, Asia, Indonesia, and surrounding islands. But not only the population will grow in these regions, countries will shift from developing to developed, and this demands more energy too. The significant factor which influences energy consumption increase is improvement of humans' life. To measure how good people live, we can use HDI, which is Human Development Index. It is estimated based on standard of living, literacy of population, educational level, and life duration. As you can see, the developing countries has smaller HDI than others. Interesting that HDI correlates with energy consumption to some extent. That is why energy consumption of these countries will grow not only because of the population growth, but also because of living standards growth. How much energy we use determines how good we live. Let's now look on the electricity production. As we can see, more than 60% of electricity produced using fossil fuels. Coal is the dominant fuel today. Nuclear share is quite noticeable, around 10%. In 2019, renewables generation, excluding hydro, surpassed nuclear for the first time. Share of hydro is high though, 16%. Unfortunately, the production from coal haven't changed since 90s. The positive trend is that the production from oil considerably decreased. Share of nuclear was declining since Chernobyl accident, mainly because of the gap in construction of new power plants right after it. We should also take into account that global energy production is consistently growing. The number of people without electricity access is declining. Was declining. I'm not sure. Does this animation work or not?
It's work, yeah.
It's okay, yeah? The animation?
Yeah, yeah.
Thank you. So the number of people with access to the electricity was declining, and it has decreased from 1.5 billion to less than 1 billion in 2016. Around 500,000 people will still remain without access to electricity in 2040. And this is a great global issue. Speaking about energy consumption, the share of fossil fuels is the same as 40 years ago, around 80%. Share of nuclear is around 4%. World energy consumption is expected to grow by approximately 1% per year. The share of electricity in total final energy consumption will increase from 18% to 27% by the middle of the century. And it will be okay if not the global warming problem. As you can see from the figure on the left, the trend in global warming is positive, and it will proceed increasing. If all countries achieve their current targets within the Paris Climate Agreement, the average warming by the end of the century will be around 3 degrees Celsius, well beyond the target of the Paris Agreement to keep it below 2 degrees. Global temperature increase will result in sea level rise, droughts, heat and floods. To keep the increase at 1.5 degrees level will require a very urgent and rapid reduction in global greenhouse gas emissions. As you may know, this year global CO2 emissions decreased because of COVID-19 pandemic. The International Energy Agency estimated that the emissions may fall by 2.6 billion tons this year. But if the world wants to achieve carbon neutrality by 2050, then it will be necessary to reduce emissions by a similar amount annually. As you can see, the major impact from the energy sector and transport. So to mitigate climate change, we need to establish ecologically clean power engineering, which is hard considering growing energy demands. But can we use renewable energy sources for that? Not really. They are low emitting, but not sufficient to cover the demand. Why? I will tell next. I will talk about the advantages, issues, and prospects of nuclear energy. On this slide, you can see what separates nuclear power from other sources of energy. The advantages of nuclear energy are the high energy capacity of nuclear fuel, low emissions, high net capacity factor, small volumes of fuel and wastes. These 4 points I will describe in detail later. Nuclear power plants don't need oxygen. For example, coal power plant absorbs about 25,000 tons of oxygen per day, which is equal to produced by a forest with size of Moscow. Nuclear power plants occupy small areas, which simplifies the physical protection of the perimeter. At least 2 times smaller than gas plants and 4 times smaller than coal plants. Around 300 times smaller than wind plants of the same power. We have big reserves up to 10,000 years, considering breeding or Fourier cycle. There are no risks associated with the storage of flammable and explosive substances in large quantities. For example, on gas and oil power plants, there are warehouses with fuel. Nuclear power plants can be used for distant heating and desalination. High-temperature reactors, which will be built in the future, could also be used for hydrogen generation. At last, nuclear industry is a good stimulator of science and technology. Nuclear fuel has huge capacity. Here you can see typical Russian VVR reactor fuel pellets made of uranium oxide. They put into a fuel rod and then a set of 312 fuel rods gathered into a fuel assembly. This is how fuel assembly looks without fuel rods. The energy produced after use of one fuel pellet of this size is approximately equivalent to produced by burning of 3 barrels, it's around 500 liters of oil, 1 ton of coal, or 480 cubic meters of natural gas. As you can see, carbon dioxide emissions are not higher than that of wind and hydro power, but much lower than that of coal. But where does it come from if these plants don't usually emit gases into atmosphere? Wind plants don't even have chimneys. All these emissions of CO2 are associated not with plant's operation, but with production of materials they made of. The next significant argument in favor of nuclear energy is capacity factor. This indicator gives the information on the average percentage of time during which power plant works at a full power. Nuclear power plants have the highest NCF of around 80%. Of solar and wind plants are 20 and 30% respectively. That is why nuclear power is the answer for high energy demand. Wastes from nuclear power plants are approximately 100 times smaller than by mass than from organic fuel power plants. But they should be handled in a special way. Here you can see the typical radioactive waste disposal places in building, dry storage, and in the ground. As you can see, nuclear power has its own advantages, which distinguish it from other sources of energy. To let you understand the full picture, I will describe the issues of nuclear power. I will discuss only major challenges which faces nuclear power from specific points of view, not considering economy and public acceptance. which are very important as well. These issues are limited amount of nuclear fuel, high-level waste disposal, nuclear proliferation and security, and risk of severe nuclear accidents. The amount of nuclear fuel is limited, and it is quite big in comparison with other types of fuel. However, to build sustainable nuclear industry, we need to think in advance about future generations. With the implementation of a fast reactor closed fuel cycle with plutonium, reprocessing and thorium fuel cycle, lifespan will rise up to 10,000 years. Lifespan of nuclear fuel is always growing due to discovery of new deposits. First group on the figure represents resources which are discovered, and their price is around $100 per kilo of uranium. Second group represents resources expected to occur in the area of existence. And the last group includes those with very low uranium concentration and those in which uranium is obtained only as byproduct. Seawater has a large potential for uranium production. However, the concentration of uranium in it is only around 3 parts per billion. Hence, 300,000 tons of water is required to obtain 1 kilogram of uranium. And according to Japanese scientists, there is a possibility to construct a reprocessing plant able to produce 1,200 tons of uranium per year at cost of $300 per kilo. It is 3 times higher than it costs today. And it is expensive now. And while there are cheaper resources, no one would extract uranium from the seawater. High-level waste is spent nuclear fuel materials remaining after reprocessing of spent fuel. Fresh fuel consists of uranium-235 and uranium-238. A ton of fuel generally remains in a reactor for 3 years. After that, uranium-238 emerges from the reactor largely intact. 25 kilograms of the initial 35 kilograms of uranium-235 will have undergone fission. The fuel waste exiting the reactor will also include 34 kilos of fission products, 10 kilos of plutonium, and 800 grams of minor actinides. All of newly formed products are highly radioactive. Activity of spent fuel is around 10 to the 13th power becquerel per kilogram, which means that every 10 to the 30th power, every second 10 to the 30th power ionizing particles emitted from it. And it is very high, and it is dangerous for living organisms. One more major consideration from a waste management perspective is the heat released by radioactive disintegration. The gradual disappearance of the radioactivity goes hand in hand with a decrease in amount of heat being released. A vitrified waste package of approximately 150 liters initially releases 3 kilowatts of energy, and it decreases by 1 order of magnitude after 100 years. And one more order of magnitude after 300 years. So dealing with high-level waste is a very long-term story. High toxicity needs to be isolated for long time periods, and it is potential burden for future generations. There are permanent repositories for all types of radioactive waste, except for high-level waste. Spent fuel is stored at nuclear power plants or at ground dry storages, which is not permanent. Geological repositories should be sealed and protected for thousands of years. That is why such projects should undergo comprehensive research. Also, there is no general solution, either to store high-level waste or to reprocess it. Today, there is a construction of high-level waste repository in Finland on Kala spent nuclear fuel repository. It is anticipated to start operation in 2020. In Forsmark, Sweden, there will be a room for over 6,000 canisters. The total length of the tunnels will be 66 kilometers, sited at a depth of 500 meters. The USA planned to put into operation repository at Yucca Mountain in 2008, but it faced licensing issues and the project was frozen. Concerning Russia, in the mid-2020s, an underground research laboratory should be commissioned in East Siberia. About 150 experiments are planned here, and only after 15 to 20 years of testing and justification of safety, the laboratory will be converted into a long-term storage facility for radioactive waste. There are several concerns relative to nuclear weapons proliferation and security. First of all, it is a fifth threat of nuclear weapon or creation of nuclear explosive devices from nuclear materials. Of course, nuclear weapons should be highly secured, and it is the prerogative of nuclear weapon states. In order to prevent the emergence of new nuclear weapon states, countries which possess nuclear weapons, there are International Atomic Energy Agency. The agency is an international organization which promotes the peaceful use of nuclear energy and prohibits its use for military purposes. The International Energy Agency safeguards is a system of inspection and verification of the peaceful uses of nuclear materials as a part of the Treaty on the Non-Proliferation of Nuclear Weapons. The international treaty, whose objective is to prevent and the spread of nuclear weapons and weapons technology, to promote cooperation in the peaceful uses of nuclear energy. IAEA takes measures for nuclear material accounting and control at every nuclear facility in the world, even during pandemic. There are also different types of physical protection and nuclear power plants, and special army forces to prevent illegal penetration, acts of air and ground terrorism. The containment of modern reactors like VVR 1200, which will be put into operation this year in my country, is designed to survive the crash of a small airplane. There is also threat of creation of dispersal device or a dirty bomb. The taken measures are prevention, detection, and response to theft, sabotage, unauthorized access, illegal transfer of the malicious acts involving nuclear material. There are radiation portal monitors, fixed, installed, highly sensitive to radiation devices. Here is transport monitor. This is pedestrian monitor. You can start notice there from now on. Also, personal radiation detectors, small portable instruments for detection of radiation which used in the airports or border crossings. All these measures help to considerably reduce the threat of nuclear material proliferation. The next concern is nuclear safety. Fundamental safety objective is protection from the ionizing radiation. In order to protect, it should possess three basic functions. Control reactivity, which means control of the fission chain reaction within safety limits. Cool the reactor core, carry the energy from the fuel, and contain radioactive substances. There are physical barriers which radioactive substances must pass to be released from the reactor. They connected in series. First is fuel matrix. Retention of fission products in the nuclear fuel itself with high melting point at around 3000 degrees. Cladding. Enclosure of the nuclear fuel in tubes. For zirconium cladding, the melting point is around 2000 degrees. Primary loop. Enclosure of fuel elements in the reactor pressure vessel, which is 20 centimeter thick, and reactor coolant system. And decontainment. Gas tight. For PWRs, it could stand inside pressure of around 7 atmosphere and the crash of a small airplane. Probability of simultaneous damage of all these barriers and release of radioactive material into the environment is very low. Unfortunately, like at every power plant, there is a risk of an accident. Usually, the risks are divided into 4 types. Anticipated personal occurrences, which are anticipated at least once during the lifetime of power plant. This probability, if you multiply it by lifetime of a typical power plant, which is 60 years, but we can round it to 100 years, you will get that once this type of occurrence will appear. Design basis accidents, the chance is greater than 1% over the life of the plant. Design extension conditions with core melt, the chance is less than 1% over the life of the plant. And design extension conditions with core melt. This is very unlikely to occur, but it could lead to severe contamination. And there were 3 severe accidents. Major accidents at industrial power plants. 3 Mile Island accident in 1979, Chernobyl accident in 1986, and Fukushima accident in 2011. Considering these 3 accidents, the probability of severe accident with core melt is 10 to the -4 power, not 10 to the -6 power. However, these are old reactor concepts of previous generation. Modern reactors has better safety systems and even systems for severe accidents mitigations, such as chlorine catcher, which holds molten fuel inside the container, hydrogen recombiners, and others. If we now look on the radiation emission from nuclear power plants and emissions associated with these accidents, they are really small. More radiation is emitted during the burn of coal, and you will get 50 times higher dose after flight from Europe to the USA than from yearly emissions of all nuclear power plants in the world. The dose associated with Chernobyl disaster is also very low. Here we can see the classification of nuclear power plants by the time of the reactor design. Generations 2 and 3 are operated today. Also, the most modern and safe Generation 3 reactors with severe accident safety systems in the project was connected to the grid recently. The first such reactor was connected in 2016 in Russia at Novovoronezh second power plant. Future reactor designs are anticipated to possess highly effective passive safety systems which will prevent the accidents. These designs are developing now under such projects as Generation 4 International Forum, INPRO project, and PRORIF project. And they are anticipated to arrive after 2030. According to the IAEA, the world nuclear electrical generating capacity is projected to increase by 90% in 2050 in the high case, or gradually decline until 2040 and then rebound on the 2030 level by 2050 in the low case. The world total electrical capacity is about 3% in the low case and about 6% in the high case by the middle of the century. The next topic I would like to speak about is the main concept of nuclear power reactors. As you may know, the reaction which undergoes inside the reactor is fission reaction, during which one nucleus is separated into two fission products and big amount of energy released. Also, around 2 to 3 neutrons are released, and this helps to create the chain reaction. By the energy of fission in neutrons, nuclear reactors could be called thermal or fast. As you can see here, thermal reactors have this type of neutron spectrum, and fission reactors are caused by thermal neutrons. In fast reactors, fission reactors are caused by intermediate and fast neutrons. The typical concepts of power reactors: for thermal reactors, it's light water reactors, and for fast reactors, it's sodium-cooled fast reactors. We can classify them by energy range of neutron contributing mostly to fission. This is neutron energy spectrum I was talking about before. By materials or specific conditions of the design. We can classified by fuel, low enriched uranium or MOX fuel, natural uranium, and others. Moderator, which slows down neutrons for thermal reactors. It's light water, heavy water, graphite reactors. By coolant, which cools the fuel core, and by reactor type. There are different reactor types developed in different countries of the world. For Russia, it's VVR reactors, BN reactors. The next classification is by generation or time of the reactor design. I also talked about it a few slides ago. According to the IAEA, there are two types of advanced reactor designs: evolutionary designs and innovative designs. And evolutionary designs is designs which based on previous designs, but with small to moderate modifications. And innovative designs, they incorporate radical changes and may require a prototype or demonstration plan before commercialization. For example, according to ProRIF project in Russia, will be built Brest OD300 reactor, which is prototype for Brest BR1200 reactor. Also, there is a very promising concept of reactors is SMR reactors, small modular reactors, which are promising because of low upfront costs. Also, they are quicker to build and easier to build. Here I will explain basics of plant operation on the example of VVR 1200. It is a pressurized light water moderated reactor. I already showed you the fuel. It's fuel pellets made of uranium oxide. They put into cladding made of zirconium, and cladding tubes are put into fuel assemblies. And 163 fuel assemblies are put into the fuel core. Here you can see it. The fuel core located here, inside the reactor vessel. The big amount of energy released here, which is cooled by coolant, which is light water. Then this light water heats the second loop of the reactor, where its vapor is being produced. This vapor spins the turbine and gives energy to the grid. After the turbine, vapor is condensed in the condenser and comes back to the steam generator, and it goes in a cycle. So this is very typical to fossil fuel plants. But the amount of energy released is much higher. Let's now look on the statistics of nuclear power in the world. Since the launch of the world's first nuclear power reactor in 1954 in the city of Omninsk in Russia, we accumulated large experience in the operation and design of nuclear reactors. Around 19,000 reactor years. New designs of nuclear facilities have appeared. and the characteristics of the existing ones have undergone significant changes. Today, there are 441 energy blocks operating around the world, and 54 are at the construction stage. According to the IEA forecasts, by 2050, the amount of electricity generation by nuclear power plants may double. Here you can see how many nuclear power plants are operating in every country. Here you can see the location of nuclear power plants around the world. The number of reactors have been rapidly increasing since 1960s and stopped increasing after Chernobyl accident. Now you can see that it has very little but positive trend. On this slide, you can see how old are reactors which we operate today. And they are quite old, and they will be put out of the operation in the next decade. That's why we need to build new reactors. And on the right side, you can see the reactors which are under construction today. You can see that China built around 10 reactors, United Arab Emirates, Korea, India, Russia, United Kingdom. Some of these countries are newcomers, like United Arab Emirates, Belarus, Turkey. Some are not. Russia is a leading country in nuclear energy. It built many reactors of VVR and RBMK types. Today there are 38 reactors in operation, 8 reactors in permanent shutdown in Russia, 4 reactors under construction. The share in electricity production is around 20%. There are 11 nuclear power plants in Russia. You can see them on this picture. And the number of different types of reactors are 23 PWRs, 13 LWGRs, 2 FBRs. These are the only operating fast breeder reactors in the world. And the reactors which will be built according to PRORIF project, Brest for the 300 is also fast reactor. More than 40 nuclear reactors will be built in the world according to Russian projects. And the share of Russia in the supply of nuclear fuel in the world is around 17%. In the supply of enriched uranium is around 40%. At the end of last year, Russia connected to the grid the first floating nuclear power plant intended for mass production, a power barge, Academic Lomonosov. Speaking about my country, Belarus, Rosatom builds 2 blocks of VVR 1200, which are generation 3 plus reactors. And the first block will be put into operation this year. In summary, to mitigate the climate change, we need to establish ecologically clean power engineering. The best way to address this issue is to combine nuclear power with renewable sources of energy. Nuclear power has many advantages which make it very competent with renewable energy. And modern nuclear power plants are safe, efficient, and reliable energy sources. Thank you for your attention, and Now I can answer your questions if you have any. Okay, so you don't have any questions? I have one more interesting thing for you.
Sorry, I think there was a question in the chat.
In the chat. Okay, thank you. As I understand, the question is about the is about when I derived this data of about the number of the reactors. Yeah, am I right?
Yes, Mr. Bahdanov, up to which date actually up to 40 reactors, up to which year, like last year, 40 reactors are active overall in the Russia.
In Russia?
In Russia.
Or in the world? You're asking about up to
overall, overall, please. Yes, overall. Right.
Overall reactors in Russia?
Yeah. Yes, in the previous slide.
Here?
Next, previous one, please.
This one? Yes?
Yes, this one. This one.
You're asking about reactors in the operation in Russia?
Yes, reactors in operation 38. Up to which date? Like up to last year?
These reactors are in operation now. This is the total amount of reactors which are in operation today.
Okay. Thank you, Mr. Bahdanov.
You're welcome. And if you want to check all this information, if it's up to date or not, or if you will need it to check it later on, you can, here I have sources of information which I used, and you can go to IAEA PRIEST platform, where you can find all this information and many more information about operating reactors in the world and under construction and etc.
Thank you, Mr. Bahdanov. I can check.
Okay, you're welcome. And now I would like, before we finish, if you don't have any questions, I would like you to give a small feedback, which all of you could see on the screen. Please, can you see my screen now?
Yes, we can see.
Please go to menti.com. You can open it with your cell phone. It is better if you open it with your cell phone. And type there this code. And please answer this question. Describe nuclear power in one word. This is very short and easy to do, and this will help to get feedback from you and to exchange your ideas about nuclear energy. Just type one word with which you can describe nuclear power, and you can type few words one by one. You see, as we have multiple answers, the word is getting bigger. Okay, I see your answers. Thank you so much. Big potential. I agree, it has big potential. And if someone wants to express ideas, it's a good time now. We can talk, we can discuss. Or if you want to discuss anything, you can write to me. I put my email on the presentation. Of course, you will get the slides and you can write me later on. And I will be on the school as well with you this week and maybe the next week, so we can discuss anything. I think that's it. Thank you very much for listening. See you later.
Thank you.
Now is lunch break, I suppose.
Thank you.
Thank you. Bye bye.